Hi, I just want to give some feedback on your part 2 of lab 2. So in this case, you were looking at several different balls that were tossed up. They stopped and then they started falling back down. And honestly, you should find that they all have about the same acceleration. Remember that you needed to plot the position, and then you needed to plot the velocity. And to do the velocity, you just say position divided by time is in a formula. So it would look something like this. You would just say position / time and submit it, and then it just fills that column out for you. So you can have the data done for you, and it's easy to do it for a couple of different objects. So to know whether something is accelerating is to make a graph of either position versus time or velocity versus time. When something is accelerating at a constant rate, the velocity time graph should be a line, and it is. If I make a graph of the velocity of the green versus time, it's obviously a quadratic, and I would want to insert a quadratic fit here. And that coefficient A is always going to be half of the acceleration. So half of the acceleration is 490 or 4.9 meters per second squared. So the acceleration would be 9.8. So this is a really good example of an object that is accelerating. So when you're asked to tell whether something is accelerating from a graph, you're either looking for a parabola on the position function or a line on the velocity function. What's nice is that the slope of the velocity, is going to be the acceleration. So if I do a linear fit on my velocity here, the acceleration was about -944, okay? So, and that was the slope of this graph. So that's what she's getting. And if there's a little bit of a difference, it's probably just from her data collection. The next thing you had to do was to determine if mass affected the acceleration of the ball. So you needed to do a velocity graph or a position graph for a couple of the other balls. And you should find that they all have about the same acceleration, barring any data collection error. They all are about 9.8. And they're all linear. So mass does not affect the acceleration of a falling object because the force that's causing it to fall is the weight, which is mass times gravity. And that force causes it to accelerate at 9.8 by definition. That's what weight is. It's the force that causes it to accelerate at the acceleration of gravity for that planet. So your weight is the force of the Earth pulling on you that will make you accelerate 9.8. So whether you're a light ball or a heavy ball, you all, even though you weigh differently, you all are going to accelerate at 9.8. So the acceleration of gravity doesn't change because the mass of an object changes. That doesn't make sense. Step back and think about that. The other thing you had to do is you had to look at the styrofoam ball. So if we look at the styrofoam ball and we plot its velocity against time, depending how well you took that data, it may have a slightly different value, okay? It may be a little bit lower. And that would not be because it has less mass, because you just told me, a lot of you got that part right, and then you would tell me it's because it's lower because the styrofoam ball has less mass. No, the problem is that styrofoam ball is much more easily affected by air drag because in fact it is light. And when something falls in real life, it's not just gravity that's pulling down on it. You also have air drag, and as it gets faster, you get more air drag. So you get to the point where the air drag cancels out the weight, and that's called terminal velocity. So in this case, that's what I wanted you to talk about, was that not that the styrofoam ball had less mass, but that air drag more than likely affected it. I hope this helps. This kind of question will be on the exam.